So this is chapter 4 review that I posted last night. Some of you may have seen it. If you didn't, that's all right. As before, I will go through these few exercises, type up answers, and then eventually I will save it and post it as PDF. And I will also post a recording. So here are exercises listed, and then here I'll be doing the answers. Now let me just check that there are no problems. Okay, don't see any problems this time. I posted the previous video, but first about 10 minutes are pretty silent. If you watch it, if you hook up to a TV, you can increase the volume level and you can hear it properly, but on computer it may not work very well. Okay, so let's start. List the types of strain in the order of decreasing energy, provide definition of each, and give an example of each one. So, in the order of decreasing energy, that means the strain of the highest energy. That will be torsional strain. And the torsional strain is due to eclipsing bonds. Bonds on neighboring atoms. So that's the definition. An example would be CH bonds of ethane. That's the simplest example. Then, in the order of decreasing energy, next would be steric strain. Now, for steric strain definition, there are different definitions. Some are more exact, some are less. Strictly speaking, steric strain is due to penetration of electron clouds of different atoms or groups. Simply, there is no enough room. So that would be actually a form of intermolecular interaction that is repulsive, where electron clouds, so repulsion, we can say, repulsion of electron clouds of atoms or groups that are too close to each other. And an example, we can say gauche. Gauche conformation of butane. And then third type of strain that is lowest in energy is angle strain. This is strain that is due to deviation from the ideal bond angle. So that's the lowest energy. Any species can easily or most easily tolerate that type of strain. And good examples would be small rings, such as cyclopropane and cyclobutane. So this would be answer to the first question or the first exercise. Next one, in the course of reaction, a carbocation is generated on a carbon of cyclopentane ring as shown below. So here you have cyclopentanol that was protonated and then loses molecule of water to give carbocation. So carbocation is generated in a carbon of cyclopentane ring. So would you expect strain to increase or decrease? First thing you have to consider what kind of strain are present in this molecule. So and we can identify two types of strain in cyclopentane: angle strain and torsional strain. Angle strain is easier to deal with because in molecule of cyclopentane, what you would do is you would make a model. It's a good idea for the exam, before the exam, to have models already previously made. That certainly saves time, particularly since time on the exam will be limited. Okay, so I can't again, I don't know why somebody else always shows up. No, that's not working. No, what's sorry? Yeah, unless you know how to solve it, then please don't make suggestions. Okay, so this would be cyclopentane molecule, and if you look first at angle strain, you can see it's there is almost no angle strain because angles are closer to tetrahedral angles 108. Now you know cyclopentane is in conformation, for example, like this half chair alternative envelope. So angle gets a little bit smaller. So, but still angle strain is minimal. On the other hand, there is torsional strain because of the two pairs of eclipsing interactions. And then there are some kind of skew conformations. Now, going from cyclopentane to the corresponding carbocation, we should use this gray atom that has angles of 120 degrees. Because you may recall from chapter 1, carbocation is planar, trigonal planar, with angles of 120 degrees. So you make 5-membered ring by incorporating such a carbon atom. This is not working very well. Okay. And so you can see now that actually we have angle of 120, where it should be 109.5. That's greater deviation from ideal bond angle. And that also affects a little bit other angles. So angle strain you would expect to increase. Now, and that also this carbocation forces these three atoms in a plane. But at the same time, we can move those too far atoms out of the plane. So you can see that we can get some sort of skew conformation. So all the conformations, we don't have any eclipsing conformations, but there are a lot of skew conformations. And with carbocation, of course, there will be hydrogen here, which I cannot show, don't have appropriate atom to show, but there will be hydrogen here. But that hydrogen doesn't interfere with anything, doesn't cause any strain. So actually, two hydrogens that would have been here in tetrahedral carbon that would be causing strain, they are removed. So some torsional strain has been removed, some has increased because of these rather unfavorable skew conformations that are worse than before. So for the torsional strain, we cannot say what is going on, whether it's increasing or decreasing, but we can say that angle strain is increasing. So the answer would be that angle strain let's see. Change in torsional strain. We can say that educated guess is it remains it probably remains about the same, or there is probably there isn't a large change in torsional strain. So that's how we would analyze a situation like this. And now next exercises deal with conformations of cyclohexane, of substitute cyclohexanes. Somebody asked why did the angle change in the cyclopentane? Because of a change from a tetrahedral carbon to trigonal planar as we go from CH2 group to carbocation. That results in change of bond angle. Again, that's chapter 1. Substituents in the most stable conformation of cis-1-ethyl 4-methyl cyclohexane are. So what are the positions of these substituents? The way to do it is you make 6-membered ring first, and so what we have is actually just the name. Substituents in the most stable conformation of cis-1-ethyl 4-methyl cyclohexane are. So the way to answer this question is you make these drawings. You start by drawing a formula of cis-1-ethyl 4-methyl cyclohexane. So you start by drawing a 6-membered ring, and since this is cis, both substituents are up, and they are in positions 1 and 4. So in position 1 and 4, or both are down, but we usually represent them up. Since they are cis both on the same side, let's say both up, we draw in positions 1 and 4 wedge bonds. And then you place appropriate substituents. So this will be carbon 1 ethyl and carbon 4 methyl. And then to make a model, you make a 6-membered ring, or maybe you already have it made. Make sure it's a chair of 6-membered ring. And then you look at the ring like this from the top. So it looks just like your drawing. And then in position, let's say on the top, this will be position 4, you place a methyl group. I thought I had another carbon. And then in the other position, so that's up. See, this is up, from your side up, and this hydrogen here is down. So up, methyl group. Here, up should be ethyl group. If just one carbon, I can add this. Let me see if I have another atom. I thought I had another one. So you make an ethyl group, that's 2 carbon atoms. It's ethyl group, 2 carbon atoms bonded to each other. So from your perspective, on this top carbon, this is up, down, bond, up is methyl group. Here, on the opposite side, position 1, this is position 4, this is 1, carbon 1, we have up and down. So on substituent up, you place ethyl group. And now you can see that one substituent is axial and one is equatorial. And you can tell that methyl group is equatorial, ethyl axial. So you flip it into alternate conformation. In the alternate conformation, methyl is axial, ethyl equatorial. And that's drawn right here. You can look at it under an angle and then make a drawing. Of course, on a test, all you would need to do is simply type up the answer the way I'm going to do it right now. So these are the 2 possible conformations. And again, just as I indicated, here they're represented in opposite order in which I came up. I first showed you one on the right, where methyl was equatorial, ethyl axial. And this is the second one. This is this one, where methyl, okay, like this, methyl is axial, ethyl equatorial. When this is the case, when we have one axial, one equatorial, and substituents are of different size, then larger substituent is equatorial. So if you had to type up this answer, this, for example, this is open-ended question where you have to type up answers, that's how you would type it up. So that's all you need to provide. So if you can actually, without the model, if you can make a drawing simply from the name, maybe starting with this drawing or directly doing perspective drawing of a ring, whatever works for you, if you can come up with the answer, that's fine. So this could be an open-ended question, or it could have been a multiple choice question. And then there would be answers like these. So correct answer would be answer D. Next, in the isomer of 1,2,4-trimethyl cyclohexane shown below, how many equatorial CH bonds are present in the most stable conformation? So this isomer is already shown. You would be given this formula if you end up with a question like this on a test. And so the way to figure out is either from this formula, you draw perspective drawings, viewing rings from the side like these, and in a drawing you flip them. Hopefully you know how to draw one chair and then flipped chair, or you make a model. So again, model like this, looking from the top, and then if this is top carbon, there is methyl group right here on the top carbon. So you place methyl group there. Then with this top methyl. Then methyl group right here. So looking from your side, it will be this methyl. It doesn't matter, this or this is the same. It's also the top. Yeah, top, bottom. And then carbon 4, one I'm holding, should be bottom, top, bottom. When you look at this conformation, you can tell that there are equatorial, equatorial, and axial substituents. Equatorial, equatorial, axial. So 2 equatorial, 1 axial. Obviously, if you flip it, axial becomes equatorial, equatorial becomes axial. You'll have 2 axial, 1 equatorial. So in the most stable conformation, we will have 2 equatorial and 1 axial substituent. And so how many equatorial CH bonds are present in the most stable conformation? There are 2 ways to look at it. One, to answer this question. One is once you identified most stable conformation, and it's shown here on the left, you know that there are 6 axial and 6 equatorial carbon-hydrogen bonds in cyclohexane. So each substituent will reduce those bonds. So in this case, if we have 2 equatorial carbon-carbon bonds, and we started with 6 carbon-hydrogen bonds, 2 were replaced by carbon-carbon bonds, that means we have 4. Alternatively, you can make a drawing. So redraw this compound. To avoid cluttering the drawing, I did not show CH3s, I showed them only as line formulas, and I emphasized CH bonds. These are the 4. Now, in the past, sometimes I asked questions like this on the test, and there are frequently students who would answer this question and say there are like 10 equatorial bonds. And to me, that was actually quite puzzling. Why would anybody come up with 10? Because it's not possible to have more than 6. So how could you come up with 10? And so I talked to those students, and what they did was they identified these 4 and counted, of course, these 4. But then each of these CH3 groups, they counted these hydrogens as equatorial. So we have equatorial methyl group, so they counted these 3, and these 3, that's 6 plus 4, 10. These are not equatorial CH bonds. Hydrogens attached to substituent on a ring, those are not equatorial axial bonds. We have carbon-carbon equatorial bond. So there are 2 carbon-carbon equatorial bonds, but these CH3 bonds, they are not equatorial. So there are 4 equatorial bonds. And of course there are 5 axial, because we have 1 axial carbon-carbon bond, and so that leaves out of 6, 1 is taken up as carbon-carbon bond. That means there are 5 remaining axial bonds. Read very carefully questions what you're being asked about so that you can answer that question. Are there any specific models you want us to build before to bring to the test? No. I suggested that you make 5 and 6 member ring, but you don't need to make anything. That's up to you. In fact, if you're really good at drawing things, you don't even need models. But very few students at this level are. Let me see here. And then question number 5. In an alternative isomer of 1,2,4-trimethyl cyclohexane shown below, how many axial CH bonds are present in the most stable conformation? So here you're asked about axial bonds, not equatorial, but axial. So again, you're given conformation, and again, you look from the top so that you match with this formula. So methyl group up, and this methyl group now should be up, not down. Okay. So now, when you make a model, let's see, like this. Yeah. This is about what is represented here. We have actually this one is this is not a chair. So. Okay, this set is on its last legs. Okay. Yeah, so this is one on the right. So you have axial with this one, and these two are equatorial. These two, 1,3 to each other. So 2 equatorial and 1 axial. That looks better than alternative. If your model is worn out like mine, you make sure that you fix it after a flip, because it's not going to simply flip and give you a good chair. Alternative is 1 equatorial and 2 axial. We are looking at more stable conformation, so that's the first one. That means 2 equatorial, 1 axial. You are asked about how many axial bonds there are. 6 to start with. 1 is taken up as carbon-carbon bond, this one. So there are 5 left. So 5 axial bonds. Okay, so that completes chapter 4 review. So are there any questions?